Welcome! In this video, we'll explore an exciting coding challenge from LeetCode, problem number 567, permutation in string. This problem tests your understanding of strings, permutations, and sliding window techniques. Let's dive into the details and solve it step by step. In this problem, you're given two strings, S1 and S2. Your task is to determine if any permutation of S1 is a substring of S2. If such a permutation exists, you'll return true. Otherwise, you'll return false. To clarify, a permutation is simply a rearrangement of the characters in S1. For example, if S1 is ABC, its permutations would include ABC, ACB, BAC, CA, CAB, and CBA. Now, in terms of input, both strings consist only of lowercase English letters, and their lengths are restricted to between 1 and 10,000. The output is a Boolean value true or false depending on whether the condition is met. Let's look at some examples to make this clearer. In the first example, S1 is AB and S2 is IBOO. Here, one of the permutations of S1 is BA, and we can find BA as a substring within S2. Because this condition is satisfied, the output is true. In the second example, we again have S1 as AB, but this time S2 is IBOAO. If you try to generate permutations of S1, such as AB or BA, you'll see that none of these appear as a substring in S2. Therefore, the output in this case is false. These examples help illustrate how the problem is checking for the presence of a permutation within the second string. Now, let's consider the third example. Here, S1 is ADC and S2 is TGA. One of the permutations of S1 is CDA, and this permutation is indeed a substring of S2. As a result, the output is true. With these examples in mind, notice that the problem requires you to carefully handle substring checks and account for all possible permutations of S1. Additionally, pay close attention to the constraints. The lengths of S1 and S2 can go up to 10,000, which means an efficient approach is necessary. Brute force solutions that explore all permutations explicitly may not be feasible. Finally, let's address some edge cases you need to consider. First, if the length of S1 is greater than S2, the result is always false because a substring cannot be longer than the string itself. Second, if S1 contains only one character, the problem reduces to checking whether S2 contains that character. Third, if S1 and S2 are identical, the result is automatically true because any string is a permutation of itself. Lastly, if S1 or S2 contains repeated characters, ensure your solution correctly handles these duplicates using frequency counts or similar techniques. Keeping these cases in mind will help you design a robust and efficient solution. To begin with, let's consider the brute force approach. The intuition here is straightforward: generate all possible permutations of the string S1 and check if any of these permutations appear as a substring within S2. The reasoning behind this is that any valid permutation of S1 will have the exact same frequency of characters as S1, so by generating all permutations, we guarantee that we find a match if it exists. However, this approach comes with significant computational overhead. Generating permutations of S1 has a factorial time complexity of O(n), where n is the length of S1. For each of these permutations, we then search for a substring match in S2, which takes O(m) time, where m is the length of S2. The total complexity, therefore, is O(n). *m, which grows extremely quickly and becomes impractical for larger input sizes. While the method is conceptually simple, its inefficiency makes it unsuitable for real-world use, especially with longer strings. Now, let's explore a more efficient solution using a sliding window with frequency counts. Instead of explicitly generating all permutations of S1, we can use a sliding window over S2 to identify substrings that share the same character frequency as S1. The key insights here are: first, two strings are permutations of each other if and only if their character frequencies match. Second, by maintaining a frequency count of characters in the current window of S2, we can efficiently compare it to the frequency count of S1. The steps are as follows: first, calculate the frequency count of S1. Then, use a sliding window of length equal to S1 to traverse S2. For each window position, update the frequency count for the characters in the window and compare it against the frequency count of S1. If they match, we can confidently return true. If no match is found after processing S2, we return false. This approach is significantly more efficient, with a time complexity of O(m). Calculating the frequency counts is O(26), a constant operation since we only need to handle lowercase letters, and sliding the window through S2 is linear in time. While this method does require additional space for two frequency arrays, this is minimal and constant, making this approach both time efficient and space efficient. An alternative to frequency arrays is to use hash maps for tracking character counts. Hash maps can provide more flexibility, especially if the input involves non-alphabetic characters or larger character sets. However, for this problem, arrays have a clear advantage. Since the alphabet size is fixed at 26 lowercase letters, arrays are simpler to implement and faster due to their lower overhead compared to hash maps. The overall time complexity remains O(m), but hash maps may introduce a higher constant factor because of this additional overhead. For this reason, we select the sliding window approach with frequency arrays as the optimal strategy. The critical insight here is that permutations are determined by the frequencies of characters, not their order. By leveraging this property with a sliding window, we avoid the exponential complexity of generating permutations while keeping memory usage minimal. This balance of time and space efficiency makes the sliding window with frequency arrays the best choice for solving this problem effectively. To solve this problem, we need to determine if any permutation of the string S1 appears as a contiguous substring in the string S2. A permutation of S1 is simply any rearrangement of its characters. For example, if S1 is ABC, its permutations include ABC, ACB, BAC, and so on. Instead of explicitly generating all these permutations, which would be computationally expensive, we can use a more efficient approach. First, we observe that for any substring of S2 to be a permutation of S1, the frequency of characters in that substring must match the frequency of characters in S1. This gives us a key insight: we can check for permutations by comparing character frequencies, rather than generating permutations explicitly. To implement this efficiently, we use the sliding window technique, where a window of size equal to len, S1, slides across S2. We'll maintain a frequency dictionary for S1 and compare it with the frequency dictionary for the current window in S2. By updating the window's frequency dictionary incrementally as we move the window, we can avoid recalculating everything from scratch and achieve significant optimization. The sliding window approach can be broken down into a few key steps. First, we compare the frequency dictionary of the initial window in S2 to the frequency dictionary of S1. If the two dictionaries match, it means that the current window in S2 is a permutation of S1, and we can return true. If they don't match, we slide the window one character to the right. When we do this, we adjust the frequency dictionary of the window by decrementing the count of the character that is no longer in the window and incrementing the count of the new character that has entered the window. This incremental update ensures we only modify the counts for the two changing characters, keeping the operation efficient. We repeat this process of sliding the window and updating the frequency dictionary until we either find a match or reach the end of S2. If a match is found at any point, we return true. Otherwise, if we finish processing all windows without finding a match, we return false. This method is not only efficient but also avoids the unnecessary overhead of generating all possible permutations of S1. Additionally, we handle edge cases such as when S1 is longer than S2, where it's clear no permutation can exist, and scenarios involving duplicate or special characters, which are seamlessly managed by the frequency comparison. The sliding window itself is a conceptual tool that spans a fixed size equal to the length of S1 and moves one character at a time across S2. This approach, combined with frequency dictionaries, is highly efficient in terms of both time and space. When analyzing the time complexity, calculating the frequency dictionary for S1 takes O(m), where m is the length of S1. Sliding the window across S2 involves processing each character of S2 exactly once, resulting in a complexity of O(n), where n is the length of S2. Thus, the total time complexity is O(m plus n). For space complexity, the frequency dictionaries only need to store counts for at most 26 characters, assuming the input is restricted to lowercase English letters. This gives a constant space complexity of O(1). Now, let's take a look at the Python implementation. We start by importing the counter class from the collections module to help us manage the frequency dictionaries. Next, we define the function checkInclusion that takes S1 and S2 as inputs. If S1 is longer than S2, we immediately return false. Otherwise, we calculate the frequency dictionary for S1 and initialize the frequency dictionary for the first window of S2. If the two frequency dictionaries match at this point, we return true immediately. If the initial window does not result in a match, we proceed to slide the window across S2. For each step, we adjust the frequency dictionary of the window by decrementing the count of the character that is leaving the window. If the count of this character becomes 0, we remove it from the dictionary entirely to keep the dictionary clean. Next, we increment the count of the character that is entering the window. After updating the frequency dictionary, we check if it matches the frequency dictionary of S1. If a match is found, we return true. Otherwise, we continue sliding the window until we reach the end of S2. If no match is found after processing all possible windows, we return false. To better understand this process, consider the example where S1 is AB and S2 is IBOO. The frequency dictionary for S1 is A1, B1. Starting with the initial window in S2, we compare its frequency dictionary to frequency_S1. As we slide the window through S2, we eventually reach the substring BA, whose frequency dictionary matches frequency_S1. This tells us that a permutation of S1 exists in S2, and we return true as the result. To further optimize this solution, we can replace the frequency dictionaries with arrays of size 26, where each index corresponds to a letter of the alphabet. This makes comparisons faster since arrays can be compared directly in constant time. Additionally, we can stop processing as soon as we find the first match during the sliding process, avoiding unnecessary calculations. These optimizations make the algorithm even more efficient, especially for larger inputs. By leveraging the sliding window technique, character frequency matching, and these optimizations, we achieve a solution that is both elegant and performant for the problem of finding a permutation of one string within another. Here, we start by importing the counter class from Python's collections module to help us keep track of character frequencies. The goal of this function is to determine if one string is a permutation of another. We define the lengths of the two strings, S1 and S2. If S1 is longer than S2, it's clear that S2 cannot contain any permutation of S1, so we return false immediately. Next, we use a counter to calculate the frequency of characters in S1, which will serve as our reference. We then initialize a sliding window counter to track the character frequencies in the current window of S2. Using a for loop, we iterate through each character in S2. For every character, we add it to the sliding window. If the size of the window exceeds the length of S1, we remove the leftmost character to maintain the correct window size. To do this, we identify the character that's sliding out, and if its count in the window is 1, we remove it entirely from the counter, otherwise, we simply decrement its count. Once the sliding window is properly adjusted, we compare the current window's character count with the reference count from S1. If they match, it means the current window contains a permutation of S1, so we return true. If the loop completes without finding any matches, we return false, indicating that no permutation of S1 exists within S2. This approach ensures that we efficiently check all possible windows in S2 while maintaining a sliding window of optimal size, making the function both concise and performant. Here, we start by importing the necessary utilities and defining our solution class. The method checkInclusion takes two strings, S1 and S2, as input. The goal is to determine if any permutation of S1 exists as a substring within S2. First, we calculate the lengths of both strings and handle an early edge case. If S1 is longer than S2, it's impossible for S2 to contain any permutation of S1, so we return false immediately. Next, we create an array, S1 count, to store the frequency of each character in S1. By iterating through S1 and updating the frequency based on its characters, we essentially create a fingerprint of S1 in terms of its character composition. Similarly, we initialize another array, window count, to keep track of the frequency of characters in the current sliding window of S2. As we iterate through the characters of S2, we add the current character to the window count array. However, if the window size exceeds the length of S1, we remove the frequency of the leftmost character in the window to ensure the sliding window remains the correct size. When the sliding window exceeds the length of S1, we decrement the count of the character that falls out of the window using s2.char at lens1. This ensures that the window count array always reflects the character frequencies of the current window of size equal to S1. At each step, we compare the window count array to S1 count using the arrays.equals method. If the two arrays match, it means that the current window in S2 is a permutation of S1, so we return true. If no such match is found by the time we finish iterating through S2, we return false. This implementation efficiently checks for permutations by leveraging the sliding window technique and character frequency arrays, ensuring that the solution runs in linear time relative to the length of S2. In this problem, we need to determine if the first string, S1, is a permutation of any substring within the second string, S2. A permutation is simply a rearrangement of characters, meaning the frequency of each character must match, but their order can differ. For example, ABC and CAB are permutations of each other. To solve this, we utilize the sliding window technique, which allows us to efficiently check substrings of S2 against S1. We start by initializing some key variables. The length of S1 is 2, and the length of S2 is 8. We calculate the character frequency of S1 using a counter, resulting in a 1, B1. The sliding window, represented by window_count, is initially empty. Then, we begin sliding the window over S2. At index 0, we add the character e to the window_count, which becomes E1. Since the window size is smaller than the length of S1, there's no need to remove any characters yet. Next, at index 1, we add the character I to the window_count, updating it to E1, I1. Again, the window size is still less than the length of S1, so we don't remove any characters. At index 2, we include the character D and remove the character E, which was at the start of the window. This updates the window_count to I1, D1. The window size is now equal to the length of S1, but the frequency counts don't match, so we continue. At index 3, we add B and remove I, updating the window_count to D1, B1. Again, the counts still don't match. Then, at index 4, we add A and remove D, resulting in a window_count of B1, 1. This time, the window_count matches S1_count, indicating that a permutation of S1 exists in S2. Therefore, we return true. In another example, where S1 is IB and S2 is IDBOAO, we start by initializing the lengths of S1 and S2 as 2 and 8, respectively. The S1_count is a 1, B1, and the window_count begins as an empty counter. As we slide the window over S2, adding characters one by one from indices 0 to 4, the window_count never matches S1_count. For instance, at index 1, the window_count becomes E1, I1, and at index 4, it becomes B1, O1. Even though the window size equals the length of S1, the character frequencies don't align. At index 5, we add A and remove B, updating the window_count to O1, 1, but once again, it doesn't match S1_count. At index 6, we add O to the window and remove O, keeping the window_count as 1, 1. Then, at index 7, we add another O and remove A, resulting in O2. Throughout this sliding window process, the window_count never matches S1_count, meaning there is no permutation of S1 in S2. Hence, the output for this example is false. For the last example, S1 is ABC, and S2 is CAB. Here, the length of S1 is 3, and the length of S2 is 12. The S1_count is a 1, B1, C1, while the window_count starts empty. As we slide the window over S2, adding characters one by one and removing the leftmost character when the window size exceeds 3, we find that the window_count never matches S1_count. For instance, even though the window may contain characters like C, B, and A, their frequencies don't align with S1_count. This means there is no permutation of S1 and S2, and the final output for this case is false. In terms of time complexity, the sliding window approach starts by computing the frequency count of characters in S1 using Python's counter. This operation involves iterating through the characters of S1 and counting their occurrences, which takes time proportional to the length of S1. Therefore, the time complexity of this step is O(len_S1). This establishes the initial setup for the algorithm by preparing the data structure that will be used in subsequent steps. Now, the main part of the algorithm involves iterating over the string S2. For each character in S2, we update the window_count counter by adding the current character. When the window exceeds the length of S1, we also remove the character that falls out of the window. These operations, adding and removing characters, are constant time, O1, due to the efficiency of hash table operations. After each update, the algorithm compares the current window underscore count with the pre-computed S1 underscore count. This comparison involves checking the frequencies of all unique characters, which takes U time, where U is the number of unique characters. Since the loop processes each character in S2, the overall time complexity of this step is len underscore S2 asterisk U. Combining this with the initial frequency count of S1, the total time complexity is len underscore S1 plus len underscore S2 asterisk U. In practice, U is typically small, such as 26 for lowercase English letters, so this simplifies to len underscore S1 plus len underscore S2. This is a significant improvement over the naive approach, which involves checking all possible substrings and has a much higher complexity of len underscore S2 caret 2 asterisk len underscore S1. For space complexity, the primary contributors are the S1 underscore count and window underscore count structures, which are implemented as counters. These store the frequency of each character and are proportional to the number of unique characters, U. In the worst-case scenario, where all characters are unique, the size of each counter is U. Beyond these two structures, the algorithm does not use any additional data structures, as it operates directly on the input strings. Therefore, the overall space complexity is U. For lowercase English letters, U is at most 26, making this effectively O1 in practical scenarios. This efficient use of space is another advantage of the sliding window approach. When comparing this optimized approach to the naive method, the difference becomes clear. A naive solution would generate all permutations of S1, which involves len underscore S1 time. Each permutation would then be checked against substrings of S2, requiring len underscore S2 asterisk len underscore S1 time. This results in a prohibitive overall complexity of len underscore S1 asterisk len underscore S2 asterisk len underscore S1. In contrast, the sliding window technique avoids generating permutations entirely and instead uses frequency counts to efficiently determine matches. This optimization reduces the time complexity to len underscore S1 plus len underscore S2, making the algorithm much more practical for larger inputs. Analyzing the algorithm further, we can consider the best, average, and worst-case scenarios. In the best case, a permutation of S1 is found early in S2, allowing the algorithm to terminate after processing only a small portion of S2. While the exact runtime depends on the position of the first match, the time complexity remains bounded by len underscore S1 plus len underscore S2. For the average case, the algorithm typically processes most or all of S2, performing sliding window operations throughout. Even here, the complexity stays at len underscore S1 plus len underscore S2. Finally, in the worst case, where no permutation of S1 exists in S2, the algorithm must process the entire string S2. Despite this, the time complexity does not exceed len underscore S1 plus len underscore S2, demonstrating the approach's efficiency in all scenarios. To understand why the sliding window technique achieves this level of efficiency, we can reason mathematically about its big O complexity. The key operations, adding and removing characters from a counter, as well as comparing two counters, are all highly efficient. These operations depend only on the number of unique characters, which is typically small, making them O1 or OU in complexity. Additionally, the sliding window ensures that each character in S2 is processed exactly once, resulting in a linear traversal of S2. Combined with the initial setup for S1, the total complexity of len underscore S1 plus len underscore S2 reflects the algorithm's linear scalability. This makes it an excellent choice for handling large inputs, providing a significant performance boost over the naive approach. When approaching this problem, it's important to avoid a few common pitfalls. First, always account for edge cases, such as when the length of S1 exceeds S2, or when one of the strings is empty. Neglecting these cases can lead to incorrect results or runtime errors. Another mistake is relying on sorting both S1 and substrings of S2 for comparison. While this may seem straightforward, it's inefficient for large strings and can cause performance issues like exceeding time limits. Instead, opt for more optimized approaches. Additionally, when using the sliding window technique, ensure the frequency map is updated correctly as the window moves. Errors here often lead to incorrect outputs. Avoid brute force solutions, such as generating all permutations of S1, since these have factorial time complexity and are impractical for larger inputs. Finally, keep in mind that the order of characters doesn't matter for permutations. Focus on frequency counts to simplify the problem and avoid unnecessary complexity. In interviews, this problem is often used to assess your grasp of the sliding window technique and frequency counting. The key is recognizing that you don't need to generate or sort permutations explicitly. Instead, frequency maps can efficiently verify if a substring is a permutation. Interviewers typically expect an optimized O(n) solution, which can be achieved by combining sliding window logic with hash maps to track character counts dynamically. Be sure to articulate the trade-offs between approaches. For example, sorting substrings is less efficient at O(n) log n compared to the O(n) frequency map method. Demonstrating your understanding of these trade-offs shows depth in problem solving. Lastly, always test edge cases, such as strings of unequal lengths, empty inputs, or scenarios where all characters are the same. This highlights your attention to detail and ability to consider a variety of scenarios. This problem is closely related to several others that also involve sliding windows and substring analysis. For example, LeetCode 438, find all anagrams in a string, uses a similar sliding window technique to identify all substrings that are anagrams of a given pattern. Another related problem is LeetCode 76, minimum window substring, which is more challenging as it requires finding the smallest substring that fulfills a condition, combining both sliding window and optimization techniques. Additionally, LeetCode 3, longest substring without repeating characters, is a foundational sliding window problem that focuses on maximizing the length of a substring under specific constraints. Studying these problems not only reinforces your understanding of sliding window patterns but also prepares you for variations that may appear in interviews. There are several approaches to solving this problem, each with its own trade-offs. One approach involves sorting. Here, you sort the characters in S1 and then sort every substring of S2 with the same length as S1. If any sorted substring matches the sorted S1, you've found a permutation. While straightforward, this method is computationally expensive, with O(n) log n complexity for sorting, repeated for each window. A more efficient alternative is the frequency map with sliding window approach. This involves counting character frequencies in S1 and dynamically comparing these counts against a sliding window over S2. This method achieves optimal O(n) complexity but requires careful implementation to ensure the frequency map is updated correctly as the window shifts. Lastly, there's the brute force method, which generates all permutations of S1 and checks if any exist in S2. While this guarantees correctness, its O(n) complexity makes it impractical for large inputs, so it's better suited for verifying smaller test cases. Another alternative, particularly for problems with fixed, small character sets like the lowercase English alphabet, is to use bit manipulation. This method involves representing character frequencies compactly using bitwise operations. Its time complexity is O(n), making it efficient for large inputs. However, the implementation can be more challenging and less intuitive, which increases the risk of bugs. Additionally, debugging bit manipulation-based solutions can be cumbersome. The trade-off here is between complexity of implementation and space efficiency. While this approach may not be the most beginner-friendly, it's a valuable tool for advanced problem-solving in scenarios where memory usage is a critical consideration. Great job! We've successfully tackled problem number 567, permutation in string. Remember the power of the sliding window technique for similar problems. Thank you for watching, and don't forget to subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!